Hello everyone, this is Alex and welcome again to the Math League YouTube channel. We'll be talking about sprint problem 30 from the April 2021 middle school test 12117. Colene, okay, wow, 15 miles. I could never run that far. She runs so that her speed in miles per hour is directly proportional to the smallest integer greater than or equal to her number of miles remaining until the finish line, and it reaches 0 the minute Colene reaches the finish line. Okay, so first things first, let's just try to understand how her race goes. So let's get a little diagram set up here. Bear with me. All right, let's draw this to represent 15 miles, right? Okay, this is Colene, right? Starting point, and in the first mile, I'm going to put these little mile markers over here for mile 1, 2, 3. We don't really care about the rest. There's 14, and there's the end of the race, right? And in the first mile, she has, well, at least 14, but not quite 15 miles left. So, okay, let's put that as a label here, right? Okay. 14 to 15, 13 to 14, 12 to 13, yada, yada. All right, this is the last mile, so 0 to 1. All right. So the floor of the number of miles left is 14. Wait, let's reread that problem. Let's make sure we're actually getting this right. Directly proportional to the smallest integer greater than or equal to. So it's not the floor, but the ceiling. I almost said the floor, but it's actually the ceiling. So her rate, then, if we look at the last mile, and we'll call her speed, her rate during that last mile, m miles per hour. Okay, m. This is going to be 13m in the third mile. This is going to be 14m, and the first mile she's going to be sprinting at a rate of 15m miles per hour, right? Really fast. Okay, first mile is 15m, second mile is 14m, third one's 13m, all the way until the very last mile when she's only going m miles an hour, right? I mean, I don't blame her. Running's hard. Now, you might be tempted to just add up all the rates, but remember, this is a sprint 30. Sprint 30s don't come that easy. But if we remember that distance equals rate times time, d equals rt, well, then we can figure out how long it takes Colene to run each individual mile. In the first mile, since the distance is always constant and she runs it 15 times as fast as the last mile, right? 15m as compared to m, well, it'll take her 1/15 of the time. Okay, so let's call this t. We'll go t over 15, and this will be t over 14, and t over 13, and so on. Great. So the second mile should be t over 14, t over 13, up until just t. You get the idea. Now, these we can add up. The times to complete each mile add up to the time to complete the race, right? So t times the quantity 1/15 plus 1/14 plus 1/13 all the way down to 1. That should be, we want that to all add up to 180 minutes, 3 hours. And remember, we don't want the value of t. That's not what the problem's asking for. And besides, that would be near impossible to calculate by hand. But instead we want, let's read this carefully, the greatest integer less than or equal to 1/10 the number of minutes it took Colene to run the last mile of the race. So in other words, what we're really looking for here is the floor of t over 10. Remember that floor is the greatest integer less than or equal to a number, right? Like the floor of 5.2 is 5, and the floor of -3.2 is -4, so on and so forth. Well, what did we call that? The time it took Colene to run the last mile of the race, we called it t, right? So now we can just solve for what general interval t lies in, between what two multiples of 10 it lies. And this is really the crux of the problem, because it involves testing out multiples of 10. So at this point, we're kind of left to guesstimate. Would t equals 60, for example, work? Perhaps, but let's test it out. Let's see, 60 plus a half. Well, this time we're going to work backwards. We'll just rewrite this as kind of like 1 plus a half plus a third, plus so on up to a 15th, because it's easier to calculate the bigger values first. This is what we want, right? 60 plus a half of 60 is 30, plus a third, that's 20, plus a fourth, that's 15. And you can keep on doing that. But see, there's a bit of a problem here. well, if we want to try and be as conservative as possible, right, let's go ahead and write out the values that we know for sure. Okay, we don't really need this. For that matter, we don't really need this either. Let's go ahead and just estimate upward, right? Let's try and find an upper bound, or no, sorry, a lower bound. We want a lower bound and show that that's above 180. We're trying to show that 60 is too much. So 60 plus 30 plus 20, these are the ones we know for sure. 15, 12, 10. Okay, and 60 over 7. Well, 60 over 7 lies between 8 and 9, right? So we'll just round that up to, no, sorry, we'll round that down to 8. It's definitely greater than 8, right? 60 over 8, that's 7.5, which is definitely greater than 7. 60 over 9 is 6.6 repeating, that's definitely greater than 6. And you've got 6, exactly, 60 over 10. Okay, well, 60 over 11, that rounds down to 5. 60 over 12 is 5. And then the rest are somewhere between 4 and 5, so they round down to 4. 60 plus 30 plus 20 plus 15, 125, 137, 147, 155, 162, 168, 174, 184. Oh, that's too much. Look at that. So 60 is too much. Could it be in the 50s? Let's make a note of this is too much. All right, could it be in the 50s? Well, if we try t equals 50 on our sum smaller than 180, then we know we have our answer, because then t would be in between 50 and 60, and the answer would be 5. Otherwise, we keep going. Well, for t equals 50, we may not be able to try a brute force tactic like before. If we're close to 180, then we might not be sure as to whether or not it really goes over. So we'll try bounding it above instead, right? We can calculate the first few partial sums like we did last time. We can go 50 plus 25 plus 50 over 3, which rounds up. We're trying to round up because we want to show it's less than 180, even if we round up, right? 17, 50 over first 12.5, rounds up to 13. And then you've got 10, and then 25 over 3 rounds up to 9. Well, something that's just over 7, 50 over 7, right? We've rounded up to 8. And then you've got 6.25, which is 7. And then 50 over 9, which rounds up to 6. Okay, let's see what happens at the end, right? In terms 10 through 15, we know that Colene can't possibly take more than 5 minutes to run each of the first 6 miles, right? Because she takes exactly 5 minutes to run the 6th mile. First 6 miles, last 6 miles, sorry. When the ceiling of her miles remaining is 10, right? So we have this upper bound of 5 times 6 for the rest of the time, right? No, it was the first 6 miles. Yeah, it is the first 6 miles, because I'm thinking in terms of minutes here. 50 minutes for the last mile, 25 minutes for the second to last. So I was right when I said first 6 miles. The first 6 miles are the fastest, right? So she can't possibly take longer than 5 minutes to run through the first 5 miles, right? So what's the upper bound we've just gotten here? 50, 75, 92, 105, 115, 124, 132, 139, 145, plus 30, 175. So now we know for a fact that 50 is too small, right? And that tells us our answer. So the actual time in minutes is somewhere in the 50s, right? And then when you divide by 10, that's going to be somewhere between 5 and 6. 50 less than t less than 60. So that tells us that t over 10 is between 5 and 6, right? And so rounding down, taking the floor, we get 5. And we're done.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.